Julia? Oh, okay. Julia first.
Okay, so I had two of them. The first one was 3.10, number 7.
What's the second one?
4.1, number 9.
Okay, so let's go over 3.10, number 7 first. Tangent 41 degree. Tangent 41 degree. Okay, yeah. See? Oh, that's why. Okay, so what you have here is basically you want to use linear approximation to find this. 41 is not a special angle. 45 is. Okay, so it's settled. I am going to use the linear approximation. Of tangent x at 45 degree. But when we do things like this, when we take the derivative and everything, we prefer radian. So let's do pi over 4. Okay, we need a point, pi over 4, tangent pi over 4, which is 1. We need a slope, that is f prime pi over 4. Oh, x. Therefore, f prime pi over 4 is secant square pi over 4, which is 1 over cosine. You do all the simplification, the answer is going to be 2. So 1 minus 1 equals 2x minus pi over 4. Clean things a little bit. That's the linear approximation at pi over 4, which is 45 degrees. If that is good, now you just want to plug in 41 degree. And again, keep in mind, you don't want to do degree, you want to do radian. So worst case, just do this. Actually, this is the worst case. So it's almost like 2 times 41 over 180 minus pi over 2 plus 1, which is 41, 90 minus pi over 2 plus 1. So we can simplify it to be this. Am I not right? Did I do the right thing? I did tangent secant square, cosine square 1/2, 2. So far, so good. Y minus 1 equals 2x minus pi over 4. 2x plus 1, no problem. 41. Oh, here's a pi. Oh, that changes everything. Okay. Okay, so I made a mistake. Here I should times a pi when I change reading. I forgot that. Other than that, everything is legit. Okay, that's number 7. One key thing here is whenever you take the derivative of this, it is going to be cosine x. But that is based on the assumption that we are using radian. If you use degree, the answer will be different. Okay, so just keep in mind every time from now on, you see the angle, you definitely transfer them into degree. Okay. Now it's 4.1. Number 10.
It was number 9.
Oh, number 9. Okay, thank you. Yes, number 9. You have something, you have something, you have something. Okay. You are trying to look for the extreme values of on the interval now we know it's standard process. Number 1, extreme value theorem continues. It's a polynomial, yes. Closed interval, of course. F prime x is going to be okay. Does not exist, never. So we only have f prime x equal to 0. So let's simplify a little bit. And sadly, we don't have better ways, so oh, it's actually not bad. So it can be factored out. Interesting. Four 41. So you have 2, x equals 15, or x equals negative 6. Oh, that's why. 2 times 2. It doesn't feel right. Is it right? Negative 3. Something is wrong. What did I do wrong? Oh, 9, 5. Okay, that's all right. B squared, 81 minus 4ac, 20 times 18, that's 360. 360 give me 441. 441 is 21 squared. Is it? Maybe I'm wrong. 9 plus this is that. 9 minus this is 12. 12. It's negative 3. Julia, did you get the same thing I get?
Kinda. I got really just mixed up with like finding the x values right there because it
It's
just
here,
keeps
right?
Yeah.
Do you have the same derivative I got? I may have made some mistake here.
I think that looks the same.
Okay, and then did you use quadratic?
Yeah, I did. I think that might be where I got messed up though.
Maybe I think I am wrong because my number doesn't match up. Did you get 18x squared from here and 9x minus 5? That looks right. Negative 9, positive 9, okay. 81 plus 4ac.
Did you forget to put the x equals 0 in as well?
Yeah, I keep it aside. I try to put everything else on this side. So I still have this one for sure. But I can't figure out what I did wrong with my quadratic formula. The number is clearly wrong. Negative 3 doesn't work. Okay. b squared minus 4ac. Okay. That's gotta be 81. It's gotta be 360. And it's gotta be 441. So no matter what, it's 21. But if it's 21, 9 plus minus 21, that's going to be 30 divided by 4, which is this. And negative 21 minus 9, that's 12 divided by 4. That's negative 3. Oh, I see. That's where I went wrong. Okay. Well, I'm getting old, so bear with me. I should do this. Okay, now everything looks right. Beautiful. Huh. Okay, that means the original thing can be factored out to be x minus 6 and no. This can be factored out to be 6x minus 5, 3x plus 1. That's going to be plus 6 minus this. Yes. Okay. So I got these two. So together we have 5 points from the critical points and 2 ending points, negative 6 and 4. The third thing is just compare them, which is going to be long. Paste. F 4, F negative 6, F 0, F 5 over 6, and F negative 1/3. This is 9. 4 square, 16, 256. Okay, that's the one. This one is going to be 9 times 6. That's 36 times 36. That's 9. All right. Five to the 4th. That's going to be 25 times 25. Am I right? No, 625. Okay, that's what I have so far. Anything can go wrong. But now let's compare who's bigger, who's smaller. I'm going to say this one is the biggest. Roughly. Okay. This is definitely big, so not this one. The smallest will be among these three. Everybody has a +9, so it really narrowed down to which one is positive, which one is negative for the crap in the front. This is roughly 1/9 plus oh, this is nice. So this one is crossed out. This one is definitely smaller. Now these two, which ones? This one is smaller or this one is smaller? Please let this one to be positive. Okay. That's basically what's happening here. Okay. The first one is like roughly this. Shit, this one's bigger. Actually, it's not that hard, so we can actually do it. Okay, minus this, minus this. The first one is going to be shit. They're close. Which one is bigger? This one is roughly 1/4. This one is roughly 1/4. Additional investigation. Okay, we're just doing it for fun. Let's see which one is easier. If I want to go from here to here, how much do I need time in order to get this? I need times 288. Oh, definitely this one's smaller. Okay, good, good. Max. Okay, that's what I got. How many of you wants to bet I get the right calculation? Let's try it, okay? It's just for fun. The rest, you can use a calculator. I think this one is too big. You're allowed to use a calculator. But I'm saying like the maximum is happening at -6. And the minimum is happening at 5/6. I got both right. Okay, are these numbers correct? Now I'm going to crunch them in, hopefully, finger crossed. This one is correct. This one's correct. Still got it. Okay. That will be how we do it. You can basically ignore everything after this. Okay, and use a calculator from there. But the last is just comparing the numbers.
Thank you.
So where do you have a question though?
I was just getting mixed up with like the last part and everything. I think I was just using like a couple round numbers.
Okay then. Did you try to do it by hand and got the arrow without using a calculator?
Yeah, I think that's what I was doing.
That's the spirit. You'll keep doing that. That's how you keep your brain sharp. All right, Austin, what question do you have?
4.1, problem 5.
Find the critical points of the function this. Now we know for critical points. Okay. Well, do you have does not exist? Will secant squared ever be does not exist? Notice that secant x is 1 over cosine. So the answer is yes, when cosine x equal to 0. That is when x equals negative pi over 2 and pi over 2, given this interval. Okay. F prime x equals does not exist. Done. Fx equals 0. That is going to be this gives you 2. Well, cosine x is 1/2. You're looking for a 30 degree, 60 degree. Eventually you realize x equal to pi over 3, 2 pi over 3, negative pi over 3, and negative 2 pi over 3. Sounds good. The rest
Yeah,
is
thank
just
you.
try to see are they critical points. You have this, you have this. Do you feel uncomfortable when you see this? And tangent?
No.
Better be now. The reason is tangent x has a vertical asymptote. Okay, at pi over 2 and negative pi over 2. Therefore, even though you got the derivative does not exist at pi over 2, it's not because it's a critical point. It's because you have a vertical asymptote. Okay, so the final answer should be only this. This is not critical. This is vertical asymptote. Okay, so the final answer should be these 4, not the negative pi over 2 and pi over 2. All right. So one thing tricky with trigonometry, that is if you have tangent especially and secant, cosecant, cotangent, you have asymptotes. So even if you did the derivative, you find it's not defined, it may be because it's a vertical asymptote, not a critical point. Okay. Adam?
Oh yeah, could you do problem 4.1 problem 14, please?
14?
Yeah.
Oh. Alrighty, we have problem 14. Check the boxes of the point where the graph have a global maximum. Just by looking at it, I would say it's at E, okay, which is highest. Check the boxes of the point where the graph has a global minimum. That will be T. Okay. Check the boxes of the point where the graph have a local maximum. Local maximum, we have E for sure. We have S for sure. The things are kind of tricky will be A. Is A a local maximum because it doesn't have a left-hand side? And also, is everything from B to D a local maximum? According to what we had in class, we should include A, B, C, and D. For local maximum, sorry. A, B, C, D. Oh, take it back. C, sorry. You're right. A, C, E, S. Okay, finally, check the boxes where the globe has a local minimum. Local minimum will be B, C, D, R, t. Okay, so I think everything you got is reasonable. Now let's see how Weber wants it. Weber doesn't want to include A. And Weber does not want to include H. Doesn't want to include T, so. Okay, so it's purely web work. What you said was correct, but just keep in mind then for web work, they don't count the ending point. However, according to what we had in class, this deserved to be a local maximum and this deserved to be a local minimum. Okay, all right. Any other questions? Okay. Now we move to 4.3. How derivative affect graphs. Basically, we want to draw a graph with something a little bit more complicated. So let me be careful here. Something like this. Think about in college algebra, if I ask you to draw the graph of this, what are you going to do? Other than, just plug in numbers and see a lot of them until you see the rough shape, right? What are you going to do? Well, usually we check the XY intercept. Okay. The second thing we do is we check the ending behavior. You may have asymptotes, you may have going to positive infinity or negative infinity. Sounds good? That's basically what we checked before. We can give a rough sketch of the graph. Now, of course, we can do more because we have derivative. We can find where your derivative is positive, which means increasing. We can find where your derivative is decreasing. We can find where your derivative is zero or does not exist. Therefore, you have a local maximum or minimum, things like that. Okay, so that's basically what we will list and add to this existing list for this section. Okay, very, very simple and intuitive. So first, what information can you get from f prime x? Number one, increasing and decreasing. How do you do it? Quite simple. F prime x bigger than 0, increasing. F prime x less than 0, decreasing. Like that. Okay, with that in mind, let's draw this. We said this is hard before. Now we can do more. Okay, example. Consider this graph here. Find where it is increasing and decreasing. All right. Now we know. You look at the first derivative. So take y prime. Moreover, you can factor them out. Do you recall how to decide if this one, the whole thing is decreasing or positive or negative? Like this. Do you recall? Do you want an explanation of how to do this? If yes, just click yes. Okay, we better do it. All right. So basically, we're trying to decide, okay, depending on which number you plug in, this one is going to be positive or negative. Okay. Now, this is what I observe. Number one, this one will be 0 at these 3 points. Sounds good? That also means when you are in this interval from 2 to infinity, you have to be all positive or negative. You cannot have both sign. Otherwise, you should touch 0 somewhere. How did you change from positive to negative or negative to positive? Make sense so far? Okay. Then that leaves us, once you list all the zeros, you only have 4 intervals. And on each interval, you just decide which one you want to choose. The good news is you only have 1. It's either all positive or all negative. They won't change sign until they hit 2. That's the first one. Okay. So how do you choose on bigger than 2? Do you have positive or negative? You simply just plug in a number. 3 belongs here, right? Then 3 is 12 times 3 times 3 plus 1 times 3 minus 2. Is this one positive or negative? Positive. It's only positive for 3. But everybody bigger than 2 should share the same sign. If 3 is positive, the whole thing is positive. Sounds good? Similarly, for the second one, you can take a test point. You can take 1. You can take 1/2, whatever, as long as it belongs to 0 to 2. You can test quickly. You can test quickly. I will leave it to you, but basically just pick the corresponding numbers. That's the first way of doing it. Second way, of course, you can list these 3 and the 4 interval. You do know the whole thing. Oh, hold on, Adam.
So are you saying it's positive or negative for the derivative graph or for the original equation?
For this.
Okay.
And that is the derivative. So positive or negative for the derivative. The reason is because we're looking for increasing and decreasing interval.
Okay, thank you.
Yeah. The second way of doing it is simply by argument. Okay, you have 3 factors, right? The whole thing is positive or negative, depends on is each factor positive or negative. Okay, from 2 to infinity, what is x? Positive. X plus 1, positive. X minus 2, positive. Okay, together, positive times positive times positive times 12, positive. Sounds good? So you can do this table. From 0 to 2, you can think about 1. Positive, positive, negative, because it's less than 2 now. Together, positive times negative, that's negative. Okay, so with this table, you can again came up with the final table of on which interval it's positive or negative, depending on each individual one. Okay, Adam? Oh, okay.
I forgot to put my hand down, my bad.
Yeah, that's fine. Sounds good. So whichever way you can do a test point, you can do the argument. Personally, I prefer this way because it's easier for me to visualize. I don't have to calculate actually the number. Okay. Moreover, there are some trick you can do. I won't introduce in class, but you notice from here to here, only one of them change sign. From here to here, only one of them change sign. From here to here, only one of them change sign. Which should make sense, right? When you cross 2, the only thing should change sign is x minus 2. Right? Everybody else shouldn't change sign. Why? Because x plus 1 change sign when you cross -1, not when you cross 2. Okay, so play with that. You will see this one in general will be very easy to do. if you just pay attention to the power here. Okay, but either way. Okay, our goal is try to produce this. Now we have it. So our answer is fx is increasing on -1 to 0 to infinity. Fx is decreasing on this and this. Is the idea clear? Okay, good. Several notes people had for me. Number one, should I say it's increasing on 1, 3 or 1, 3? Okay, see the difference? Do you include 1? Is it increasing at 1? Well, technically, we take this one. This one makes sense. Just by convention, we take the first one. So whenever you do increasing or decreasing, always take parentheses. The ending points, it doesn't make much sense to talk about them. Okay, that's number one. Number two, I wrote like this. People will argue, why don't you write like this? See the point? Which one is more reasonable? Let me give you an example. Okay. Do you think it makes more sense to say this one's increasing on this? Or do you think it's more reasonable to say it's increasing on this? Can you see this is actually the only choice? Because when you say union, you put them into a whole region. If you put it in the whole region, you're saying it's increasing here and it's still increasing. That means this one is on top of this. That's when you can use the union. Because you keep increasing, that means everything on the right should be bigger than the left, right? So if you use the union, they become one answer. That means what happens at 3 should be bigger than at what happens at 2. But if you use comma, this part does not have to have anything to do with this. Okay, that's the major difference. That's why I used comma. So you can use the union if you have this case. But in general, this is safer. Okay, that's roughly where the question comes from. I think that's really, really good question. All right. Back to the example. That's how we figure out it's increasing or decreasing. Okay, why are we doing that? We were trying to do the graph. Can I do the graph based on this? Of course. That's the graph. Sounds good? So you can see when you know it's increasing or decreasing, you do know better about the shape. Of course, you can add in the y-intercept, x-intercept to make it more accurate. But this one roughly tells you the shape. 2 more things we'll observe from this. Number 1, once you can do that, do you see that you already have the local maximum and minimum? Okay, so we have a new way of quantifying local max and min, which is called the first derivative test, which is quite simple. If you test your f prime x, you have the following situations. This is your C. It was increasing before, decreasing after. This implies you have a local maximum. If it's decreasing before, it's increasing after. This implies you have a local minimum. That means once you have the table, you don't have to bother to, in addition, find local maximum or minimum. It's there for free. Okay. What about this case? Do you remember what they're called?
Saddle point.
Saddle point. Great. Okay, that's everything about first point, the first derivative test. Really, really easy. Okay. Any questions so far? All right. Are you happy with the graph? It's ugly. Why? I prefer something nice. Curvy, smooth, things like that. Okay? So can you see that? Just knowing something is increasing only tells you the trend. It doesn't tell you the shape, roughly, right? So can we do something in addition to tell what the shape is to make it smoother? For example, I know it's increasing, but you can increase like that. You can increase like that, or you can increase like that, or a combination of that. Sounds good? By a simple observation, you realize this one is nothing but two of these, just on different interval. So fundamentally, you only have three cases. You either increase like this, or you increase like this, or you increase like this, or you can paste them together like that. Okay. Good so far? How can you tell which case you have? They all have f prime x bigger than 0. All the three of them. So f prime x is not enough. Okay. Let's talk about this case. It's increasing. Everybody agree? Is the rate of increasing getting steeper or flatter? Flatter. Okay. Getting flatter means what? Means the derivative is getting smaller. Make sense so far? So if I'm going to write it down, for this case, your derivative is actually going down because you get flatter, flatter, flatter. On the contrary, this one is getting steeper and steeper and steeper. This one goes up. What about a straight line? Well, your derivative stays constant. It doesn't change at all. Good so far? That means your derivative of this one is increasing. How do you show something is increasing? That means its derivative is positive, right? How do you show f prime x is increasing? That means the derivative of f prime x is positive. What is the derivative of f prime x? That's the second derivative. So saying that is saying f prime prime x is bigger than 0. And f prime prime x is 0 means f prime x is constant. Good so far? So we can tell the information if we push it to the second derivative. Okay. Second derivative is not used to decide are you increasing or decreasing. Instead, it's used to decide do you have this shape or that shape? We will give them a name. It's called concavity. we have concave up corresponding to positive second derivative, and concave down corresponding to this case. This is concave up, which means you increase like this or you decrease like this. This is concaving down. You increase like this or you decrease like this. Some people call this a cup case, and this is a cap case. Sounds good. All right. Second, you know when you have f prime x, you have something change from positive to negative. That's where your f prime x change sign. You have local max. You have this. You have local minimum. That's where your function changes its behavior. Similarly, for f prime prime x, you also have where it changes sign. What's the graph look like? You went from concave up to concave down. That's where the point is. Okay? You went from concave down to concave up. That's where the point is. Sounds good? We call those inflection points. We don't differentiate between going from positive to negative or negative to positive. We just call them inflection points all the time. That corresponds to where your f prime prime x change sign. First derivative change sign, local max, local min, or saddle point, which means don't change sign. Second derivative change sign, inflection point. Good so far? Finally, we have the so-called the second derivative test. I'm listing a lot of simple facts here. Later, we will write them into a table so you know how to start and how to end. You have 5 things to look for. Okay, but for now, let's just write them down. It all narrowed down to, if you already know f prime c equal to 0, that means you only have 3 choices. You either have a local max, or you have a local minimum, or you have a saddle. Local max look like this, local minimum look like this. Always. Do you realize you can connect this one with concavity? Which means local max always concave down. And local minimum always concave up. You cannot have a local max meanwhile concaving up. It's not gonna happen. Sounds good? Okay, so if it were me, I would just put a table here. If f prime c equals 0 and f prime prime x less than 0, local minimum, maximum. That is called the second derivative test. So now you have 2 ways of testing something's local maximum. First way, try this. Second way, try this. They do the same thing. Okay. Which one is better? This one you only need to compute f prime x, then figure out positive or negative. This one you need to compute additional second derivative. Can you see this one is better in terms of speed? You already have f prime x. Okay. Second, this one can handle the case where f prime x equals does not exist. When it does not exist, you can still have positive to negative, negative to positive, right? But for does not exist, this case cannot cover because your f prime c has to be 0. If your derivative does not exist, there's nowhere to find your second derivative. Sounds good? So in all kinds of ways, this way is better. So in our class, we go with this. Unless I ask you to use the second derivative test. Otherwise, always stick to this. It's easier. Sounds good? So why do we introduce this? This becomes nice when you go into 3 dimension. Okay, in that way you cannot tell. For example, let's say you have a bowl. Okay, clearly the local minimum is actually at the bottom of the bowl. Sounds good? How do you tell it's a local minimum? You cannot tell, well, it's negative some way and positive some way, so it went from decreasing to increasing. It really depends on which direction are you talking about, right? However, if you want to do the second derivative test, it's easier in that way. You just calculate the matrix. So this is actually for higher dimension. Lower dimension, the first way is better. Sounds good? All right, that's all for today. Tomorrow we go over examples. Before you guys go, I received an email from the provost saying that we need to do an election day adjustment. Okay, so